All right, guys, so here we are. We have these equations, and maybe for future reference, I will number them. So 1, 2, 3, and 4. So let's see what happens. Let's see what happens with these equations. If we consider the first two equations and do something apparently clever with them. So what exactly? So if I take the first equation and multiply it by alpha, take the second equation and multiply it by beta, and then I will add them together. So I'll take the first equation multiplied by alpha. I will get alpha sigma I alpha squared alpha w I alpha squared p. Take the second one, I will get sigma beta alpha beta beta squared. Obviously, it is not going to change any of those equations because alpha and beta are constants. And then I add them together. And if I do, I'll get something interesting. I will get sigma alpha u plus beta v plus I alpha u bar alpha u plus beta v plus alpha w du bar plus I alpha squared plus beta squared p hat. Okay, are you with me? Okay, so that's very simple. Now, what we observe that there is a combination which is repeated. And that brings us to a clever idea that is not my clever idea. It was actually introduced for the first time in early 1930s by a man known as Squire. And what we are dealing with here is later was named after him. It is Squire's transformation, which will eventually lead to Squire's theorem. So, alpha u hat plus beta v hat. Let me call this alpha tilde u tilde. Now, clearly, this is what we have, and this is just a formality, because any function could be written as a product of arbitrary constant, which is alpha tilde, and some other function, u tilde. So there is no limitation there. Okay? We don't say what alpha is at this stage, but we just notice that this whole thing is alpha. We just write it as alpha tilde times u tilde. And this is always possible to do. But what about alpha tilde itself? Well, what I will do, I will also introduce alpha tilde squared as alpha squared plus beta squared. And you can see where it is coming from. Okay? So then I will get the following expression. So I will have sigma multiplied by alpha tilde u tilde plus I multiplied by alpha u bar alpha tilde u tilde. Right? So far so good. Plus alpha w hat. Multiplied by du bar. Plus I alpha tilde squared p hat. Agree? Now, you can see everything is sort of good except we have alpha and alpha tilde mixture. So, how about I divide by alpha? And let us see what happens. If I divide by alpha, I will get alpha in the denominator in the first term, and this guy will disappear. And so will disappear this guy, and that will be alpha. Okay? So, I will introduce another thing just to hide this alpha. So, I will introduce sigma tilde, which is equal to sigma alpha tilde divided by alpha. Okay? So, and if I do so, I will get, so now I don't need this. And this is simply sigma tilde. Okay? So sigma tilde, alpha tilde, so that has not been changed yet. And well, we did this trick here, so we might as well do the trick here. So we will introduce alpha tilde divided by alpha p hat is equal to p tilde. And then this becomes p tilde. This disappears, this disappears, this disappears. Agree? All right, so I did something, well, so far it seems to be trivial, so, but we'll see if it will lead us any further. So now we have a mixture of tilde quantities and hat quantities, right? So we still have w hat, right? So what I will do, I will formally declare that they are the same. And if I do so, that becomes tilde. All right, so we've done that, and so far so good, but I already transformed most of the quantities, except it does not appear here, but V is also going to be transformed once I start working with the other equations, so I might as well add them, the definition for V, redefinition of V at this stage. So I'll just call that V. Whenever we encounter that, we will know that the V hat and V tilde are the same. So I pretty much what I try to do is to write everything in terms of tilde quantities. Okay. Now, let us look at a set of previous equations. And the previous equation now We took care about this pair of equations, right? We still have these equations here, sitting here. So let's look at this equation next. So if we take this equation, it contains head quantities and alpha, right? So what I would like to do is to take this equation and multiply it by alpha tilde divided by alpha. Clearly, alpha tilde and alpha, they are constants, so the ratio is a constant, so therefore I'm taking this equation multiplied by a constant. It does not change, right? And if I do so, so I will get, let me just correct my. So if I do so, I will get sigma w, now it is tilde, plus I alpha tilde u bar w tilde is equal to minus dp tilde. It's just a formality, so let me go back and see what happens. So if I multiply by alpha tilde and divide by alpha, so I will get sigma multiplied by alpha tilde but divided by alpha, which is sigma tilde, right? If I multiply by sigma tilde and divide by alpha, alpha will disappear and alpha tilde will appear here. I said that w hat and w tilde are the same, so therefore I just changed the notation. And if I have p hat multiplied by alpha tilde divided by alpha, we called it p tilde. So everything is consistent. So therefore, what I've done here, what I achieved here, I wrote this equation in terms of tilde quantities as well. Now let's look at the last one. This one. And I alpha u plus I alpha b v, we already know what that is, right? So this is nothing else but alpha tilde u tilde plus dw tilde is equal to 0. Agree? So now what I've done, I rewrote the system in terms of tilde quantities. Say it again?
That in that equation it will be sigma tilde. So in this equation, first one. Yes.
All quantities are tilde quantities now. Okay? If I miss something, so they're supposed to be all tilde quantities. So what we introduced here is known as a set of Squire's transformations. It's just algebraic substitution. But guess what we achieved? How many equations, tilde equations, do we have now? Remember, we had 2 of those, but we lumped them together. We added them together, so they are lumped together. So therefore, our system of equations now, and I will write it explicitly on the next slide, is sigma u tilde plus I alpha tilde u bar u tilde plus w tilde d u bar plus I alpha tilde p tilde is equal to 0. That's the first equation. The second equation will be sigma w tilde tilde plus I alpha tilde u bar w tilde plus dp tilde is equal to 0. I alpha tilde u tilde plus d w tilde is equal to 0, and sigma tilde v tilde plus I alpha tilde v tilde plus I beta p tilde is equal to 0. All right. So we had four equations. Sorry, we had yes, we did have four equations. So we reduced those equations by lumping two of them together to a system of these three equations, but we still have the very first equation, the second equation, which is written in a transformed form like that. What's interesting about this system of equations? So is it clear where this comes from? Should I just go back? That's this equation, so it was originally there. So what I did, I replaced these two equations with the sum and still kept the second of the equations. Except I rewrote this equation in terms of tilde quantities as well. Is that clear? So what I did, I replaced the first equation with the sum, but I kept the same the second equation as is and simply wrote it last. Is that clear? Okay. Now, why did I put this dashed line here? Can you see why? Can you explain why?
Where will be for
because of beta, the answer to
We'll check out the variables. So what variables is included in the first equation? What is unknown here? Tilde, u tilde, u tilde, w tilde, p tilde.
so
Right? What's the second equation? W tilde, w tilde, p tilde. What's that like for? U tilde, w. Is there v tilde?
done.
No. So therefore, this system contains three unknowns: u tilde, w tilde, p tilde. There are three equations, three unknowns. We can solve this. So we can solve 3 by 3 system. And then once we determine p, we can substitute it there and find the v. So rather than solving 4 by 4 system, we solve 3 by 3 system and then plus 1, which is much cheaper. Right? And you can see why that is cheaper, simply because if you imagine 4 by 4 matrix, what is 4 by 4 matrix? 4 by 4 matrix contains 16 elements. What is 3 by 3 matrix? 9 elements. So inverting a matrix which contains 9 elements or inverting the matrix which contains 16 elements, what is cheaper? Right? So clearly 9, and significantly cheaper. So therefore, it is much easier to invert matrix 3 by 3 plus solve extra equation, rather try to invert matrix 4 by 4. Okay, so that is the gain here. So therefore, that is what we will do now. So we will be able to solve this. And once we have these tilde quantities, we substitute them here. We will get v out of the last equation. And then, of course, we can, if we need the original u, v, w, and p, we can always just use algebraic substitution, back substitution right? So it's not a problem at all. So that's how it works. So that is the reduction of the numerical complexity, essentially the reduction of a 4x4 system to 3x3 plus 1, which is much cheaper. But that is not the only and probably not the most important thing which we can deduce from here. So let us be a little bit more observant here. So remember that my original assumption was that the solution is written in this form. So this sigma quantity here, this is generally complex number. Sigma is not necessarily real. So therefore, the solution is proportional to e to the power sigma t, which is really e to the power sigma r plus I sigma I multiplied by t. So that's the general representation of a complex number. It contains real part and imaginary part. So e to the power sigma rt will be responsible for telling us whether this solution grows or decays. And e to the power I sigma it will be responsible for telling us whether the solution oscillates or not. Okay? So the two parts play different roles. So essentially this is growth rate and this is the frequency of oscillations, all lumped together in one complex number. Very convenient. But now let us consider the case of unstable flow. So what does that mean? If sigma r is greater than 0, unstable basic flow. I will use BF for denoting basic flow. Is that clear why? Because if sigma r is positive, then this exponential function will be growing. And this exponential function is responsible for describing perturbations. If they grow, it means we are going further and further away from the base flow. It becomes unstable. We cannot see it. It will be modified. Okay, is that clear? Okay. But sigma r is equal to alpha divided by alpha tilde sigma tilde r. Right? Where does that come from? So it's easy to see. That's this. So essentially what I do, I will just invert this. Okay? And of course, this is a complex quantity. In particular, this relationship will work with the real part of that quantity. Okay. So I will write this explicitly. This is alpha divided by alpha squared plus beta squared, square root of that. Okay? What can you say about the size of sigma r and sigma r tilde? Can they be equal to each other?
Can this be equal to that?
What do I need to achieve? What do I need to require in order for this to be the case?
What it is.
So the only way this is equal to that, if this coefficient is equal to 1.
Yes.
This coefficient is equal to 1 only if beta is equal to 1.
Right? So if beta is equal to 0, then this and this will be the same. But what if beta is not equal to 0? Which one is larger? So this one will be multiplied by the quantity which is clearly smaller than 1. So therefore, this one will be always smaller than that one as long as beta is not equal to 0. So let us now make a physical conclusion out of this algebraic observation. So sigma tilde r is obtained essentially from this set of equations. Agree? This set of equations does not contain v. Agree? V is not there, like v is equal to 0. Right? If v is equal to 0, then, then obviously it cannot be present in the system, and we do not see it here. So equivalently, we can say that this equation, this set of equations looks like v is equal to 0. Is that correct? Can you see that? Right? If v is equal to 0, then in this equation, beta is equal to 0. So if v is equal to 0 and beta is equal to 0, then the last equation is also true. But what actually happens is if v is equal to 0 and b is equal to 0, what sort of flow does that describe? Remember v component. In which direction is it? In y direction, right? And what is beta? Beta is periodicity parameter. Periodicity in which direction? In y direction. So if beta is equal to 0, then periodicity in y direction is gone, right? It's just constant in y direction. And if v is equal to 0, there is no flow in the y direction. Agree? So if beta is equal to 0 and v is equal to 0, we have truly two-dimensional perturbations, which means the perturbations, they behave non-trivially in time, and they behave non-trivially in x direction. So they have periodic wave in x direction. Alpha is not equal to 0, so they are periodic in x direction, but nothing happens in the y direction. Nothing at all. Right? So, and if for some reason you would like to insist on looking at what happens in the y direction, right? You just say, well, I insist that my perturbations, they will propagate in x direction and also do something in y direction. So therefore, essentially, they will be propagating under some angle. Remember, x direction is the direction in which the main flow occurs, base flow. Okay? So, and if we insist on the situation, considering the situation that the perturbations somehow propagate or exist in the direction perpendicular to the main flow direction, when beta is not equal to 0 and v is not equal to 0, perturbation v is not equal to 0, then we conclude from here then the growth rate of these truly three-dimensional perturbations is going to be smaller. Is that clear? Because this is three-dimensional case. Sigma r is sigma which belongs to the original problem, and the original problem is three-dimensional problem. So sigma without tilde is what we will observe in fully three-dimensional case. When beta is not equal to 0 and v is not equal to 0. Agree? Okay. But tilde is what happens when beta is equal to 0 and v equals to 0. So it turns out that sigma tilde, which corresponds to beta equals to 0 and so two-dimensional case when perturbations are chosen to propagate in the main flow direction, is always greater than perturbation growth rate of three-dimensional disturbances. That is fundamental physical conclusion. It means that if the base flow we choose indeed is unstable, the modifications will occur in the direction of the main flow, but not across. And that means that at any point in time, we will be okay by considering two-dimensional problem from start to finish. Because we know if anything bad happens to the base flow, this will happen in its own direction, not across, because of that. And this is very powerful conclusion, which is known as Squire's theorem. And it is stated that for the flows that we considered here, U is the only non-zero component of the base flow, and it is unidirectional, essentially unidirectional flow. Then perturbations might destabilize it only if they propagate, or destabilize it first only if they propagate in the same direction as the base flow. So therefore, we don't really need to consider three-dimensional flow. And even though I started with this system of 4 equations, from the very beginning, I can set V equals to 0, get rid of this equation completely, and only focus on this, this, and this. And what I obtain will be physically relevant, because instability, if it occurs, it will occur along the main direction. It will not occur across. Very powerful conclusion. Okay. So what we need to take out, the message that we will take out from here is the following. So first, we need to know the set of transformations. So these are just algebraic transformations. And they are known as Squire's transformations. And sigma r, which I say it is 3D, is less or equal to sigma tilde r, which is 2D. So three-dimensional disturbances, this is Squire's theorem. So Squire's theorem tells us that physically what happens, that if the flow is to be destabilized, this destabilization will happen along with the flow itself, not across. Two-dimensional disturbances will be always the most dangerous, the ones which will spoil the original base flow motion. That's what happens. So, but once we showed that, we're actually stepping in the all new territory, because now we have a lot more freedom in terms of how much time, how much mathematical effort we can invest in investigating this problem further, because we know that we only need to do we only need to investigate two-dimensional stability, not three-dimensional stability. And the main reason why it was so important, well, definitely in 1930s and probably up till 1980s, because computational power was not there. Computing power was not there. Computers were not strong enough. So therefore, considering anything three-dimensional pretty much was off the limits. Two-dimensionality was two-dimensional problems probably were solvable starting from late 1970s, 1980s in some cases. So right now, of course, three-dimensional solutions are possible, and pretty much nobody worries much about laminar flows in 3 dimensions, so that's assumed to be doable computationally. But at that time, no, it was impossible to solve 3-dimensional problem on those computers, and let alone by hand. So that's one thing. The other thing is that if the flow is 2-dimensional, it can be described using stream function. And I very briefly mentioned that in the yesterday in the beginning, probably in the second hour of our lectures, stream function. So now we can describe the flow and what happens to it in 2 dimensions by introducing this stream function. So why is it important? Why is it convenient? Well, if somebody thinks that still thinks that it is actually cheaper, well, no, not really, because you cannot lie to nature. You cannot fool the nature. If the nature stated that price is such and such, no matter what you do, you will pay that price. You just will have to pay in different notes. But the sum will be the same. So what you will do, you will get rid of, by introducing the stream function, you will get rid of one of the equations. The continuity equation will be gone, but you will introduce higher order derivatives in the equations. And higher order derivatives require more boundary conditions. So you get rid of continuity equation, you enjoy that, but then you have to introduce extra boundary conditions, which are extra equations. So now, but nevertheless, from an algebraic point of view, stream function does provide certain benefits, but only a stream function can only be introduced if the flow is two-dimensional. So, question. So I forgot to talk about that last time. I mentioned the stream function. But is it clear why stream function can be introduced only in 2 dimensions, not in 3 dimensions? Have you ever heard this discussion explained that? Have you ever been explained why this is so? No? So I'll give you one of the possible interpretations. So consider the continuity equation, right? By now you know what I mean. When I talk about continuity equation, it is actually incompressibility condition, right? So, but I will call it continuity equation because it is traditional, right? It's not accurate, but it is traditional. So continuity equation in 2 dimensions, how many terms do we have? 2. What about 3 dimensions? 3 terms, right? So, and what is on the right hand side of the continuity equation? 0. So, if you have 2 terms, what can you conclude about these 2 terms? So, if they add to 0, the only way to do that is to make sure that one term is exactly the same as the other but has an opposite sign. There is no absolute ambiguity here. You cannot do it any other way. That's the only way possible. Now let's consider 3 terms. And they add up to 0. But there is a lot of ambiguity how you can do it. So in infinitely many ways you can add 3 terms together and get 0, right? So one could be 0, the other 2 opposite to each other. Then the second one could be 0, and the first and the last one could be opposite to each other. Or the first could be equal to 1, and the second that it could be -1/2 and -1/2. And so on and so forth. So therefore it is ambiguous. You cannot uniquely solve this problem. Remember that the introduction of a stream function tries to get rid of the continuity equation, and therefore it is possible to do in a non-ambiguous way, unique way, if we have only 2 terms to deal with. But in 3 dimensions, you have too many options, infinitely many options, so therefore you can't really do that. So that is one of the reasons, it's not the only one, but the main reasons why it is not going to work. It's just ambiguous. Ambiguity means subjectivity. You do one thing, I do another thing, and our results are completely different. So who is right, who is wrong, then it's pretty much my word against yours. So that's the one way of seeing why a stream function cannot be introduced in 3 dimensions. The other thing is, so I forgot to check with you, but do you actually know the reason why it is called stream function? So obviously we know, I showed you how to introduce that, but is it clear why is it called stream function?
So of the three particles in stream, so that's it.
So stream function is one term. The other term, which is common in fluids, is streamline. So what is streamline?
The path is an to the rate of
So streamline is not the path.
Streamline is the instantaneous line which is parallel to the local velocity at every single point. Obviously, velocities change with time, and so do streamlines. It's instantaneous. So if you have a snapshot of a field, right, frozen in time, then if you draw the line, carefully draw the line which is parallel to the local vectors everywhere, that's what streamline is. If we have a steady state flow, then of course streamlines will be frozen. They will not change, they will not flip the flop or anything like that. They will be just essentially the same as path lines. But for time-dependent flows, path lines and streamlines and streak lines and all other lines, they are all different. Okay, so therefore, what we will rely on is using the stream function, knowing that it does two things. First, it gets rid of one of the equation at the expense of introducing higher derivatives, but it will get rid of this equation here. And the second thing, it will define streamlines. So streamlines are essentially level lines of a stream function. So question, do you know what level line is, or contour line? How do we get it? If we have a function psi, for example, how do we get an equation for a level line? Which parameter?
We have a function x squared equal to y squared.
What is the level line for this? What's the equation for the level line of this?
The answer to the zero.
Circuits concept x squared.
Check the equation, I'll trade the equation.
So the function is x squared plus y squared. The better variables next to 1. X squared not y squared equal to some of me,
X squared plus y squared, so function is equal to what?
Something say used.
Yippee.
I get that at most.
Constant, right? Constant. So constant, because level is a constant, right? Well, and look at the map. So what is the control line on the map? It's a level. It's actually points of equal elevation, right? That's what that is. So contour. So therefore, equation for a streamline is, if we have a function stream function of psi, then equation for a contour line for psi will be psi equals constant. Okay. So, and what do we know about the direction of the gradient and the direction of a level? So if we have gradient of a function, it defines certain direction. So if you look at the map, you will see all these double lines, which are essentially elevation lines. So if you take the gradient of an elevation function and then put it on the map, so direction of this z gradient vector, so what would be the orientation on this direction?
I go to this.
So let me just create a page here so that we will discuss that. So what we have here is a stream function. So, and remember, u is equal to d psi d, and v is equal to d psi d. So what is here? So if we have x and y, so what goes here? Y. And what about here? X. And there will be minus somewhere. So here, there, where? Here, right? Okay, that's standard, even though you can, nothing will change if you put it there, but standard one is that. Okay. So now, gradient of psi. How is it defined? Dip psi.
Someone that is due to Python.
Then we find it.
Right? So let's compare what that is. So dip psi by dy, which appears here, it is actually u. Minus dip psi by dx is v, so it is v. Now, you have a vector v, you have gradient of psi, dot product between the two. U, v, dot minus v, u. Clearly, u times minus v plus v times u, 0. Dot product is equal to 0, which means what? Perpendicular, right? So therefore, velocity vector is perpendicular to the gradient vector. My question is, if you have contour lines of psi, psi equals c1, psi equals c2, psi equals c3. So these are contour lines. What is the direction of the gradient vector? So I take a point here. So how will gradient look? No, it will be in the surface. It will be completely two-dimensional. So if you stick it to dimensions, everything will be as a plane. Yeah, but what is the implication? So in a vector. So because gradient is compared to components, so it is a vector. But what's the orientation? Enter? What does gradient? What is the meaning of the gradient?
Change.
Change. So gradient corresponds to change because it consists of derivatives. If change is not there, then gradient is equal to 0. Huh?
Let's do it again.
So you say tangent. If I'm going along the level, will I experience any change? No. So therefore, in this case, I will have no change. So, but gradient actually, the meaning of the gradient, if you forgot that, if you never studied vector calculus, the meaning of the gradient is to specify, so what it does, it specifies the direction of maximum fastest increase of the function. So if you are going along the level, you do not change anything at all. So change is 0, so therefore it cannot be gradient. So gradient necessarily is perpendicular to the levels. So the gradient is like that. That's the gradient. So the contour and the gradient, they form angle of 90 degrees. So it is not tangent, it is normal. So now, what we see here, that gradient is this vector, and we also showed that velocity is perpendicular to this gradient. So if it is, this is the gradient, and what is the direction perpendicular to the gradient? Well, this is the tangent, right? So this is gradient of v, of psi, sorry, gradient of psi, which is also normal direction. This is a tangent direction. So the tangent direction along this streamline. So this is the direction parallel to the velocity. And this direction happens to be parallel to the contour line of a stream function. So therefore, this is a stream function. Streamline. Contour line of a stream function is a streamline. That's the line along which the velocity, the fluid flows. Okay, so that's something to keep in mind. All right, so I'm sort of off track because that's sort of a prerequisite material, and but I don't mind. So that is important thing to remember physically, what stream function is and what it represents and why. So stream function, or level lines of stream function, contour lines of a stream function, they correspond to streamlines and streamlines are the lines along which the fluid flows. So that's what that is. Okay. So in our case, though, we have U component and W component. V component is equal to 0. So therefore, stream function now needs to be redefined slightly, but it, in a trivial way. So we will say that U is still d psi by d. So we have x and z directions, no y direction anymore. So therefore, d psi by dz, and W, and we are talking about perturbations, W will be equal to minus d psi by dx. So if we decided that U prime and all other prime quantities are written in a separable form, we will write that psi is also equal to something which we say call, if we used hats, so let's use hat here as well. Okay, so that is essentially the same thing as before, except I simplify our notations now. So I will not use tildes. We already decided that we are dealing with two-dimensional problem, so therefore I will just ignore the existence of y direction completely, and therefore I don't need to introduce those tildes anymore. Is that clear what I'm doing? Just to simplify writing. So therefore I will have periodic direction which is aligned with the direction of the main flow in the x direction. Nothing happens in the spanwise direction, and there is some variation in the z direction between the plates, and of course there is some sort of assumed exponential behavior of in time, and that exponential behavior consists of growth or decay, that's the first part, and potential oscillations. Okay, so that's the frequency, that's the growth. Okay. So, and in this case, we will be able to say that U is equal to U prime. How is it written? So you take that and you differentiate it with respect to Z. So what you will get is d psi hat multiplied by e to the power I alpha x plus sigma r plus I sigma I t. Agree? And what can we say? So this is U prime. And what about W prime? It is minus, what is it? So you differentiate that, so psi hat of z is still there, it is not going to change. Then it will be e to the power I alpha x plus sigma r plus I sigma I multiplied by t. And when we differentiate with respect to x, we will get I alpha, right? So it's really I alpha. So therefore, we will see that this is nothing else but my original function psi, right? So all this is exactly the same as what we had before, except it is multiplied by minus I alpha, right? Right, so yeah. Agree? Oh, to be consistent, let's just put primes as well everywhere. Okay? So these are notations. Okay. So, what can we do with all this? Now, what we will do, we will ignore this equation completely. We will deal with this system of equations, except we will not write tildes anymore. So we will just start with the work with these equations without any tildes. Oh, by the way, that's tilde as well. Without any tildes, so ignoring this completely. And if we do so, we should arrive at the following conditions. So let me just see what we start with. Well, what I will be able to do is to write explicit expression for P just from here, right? So first thing is that, well, I can see that I have derivatives of pressure here, but I don't really need to solve for a derivative here because I can find it from here. If I know everything here, so I will be able to find P directly from here. So that's sort of a bonus. So if I know U and if I know W, then I will be able to get pressure straight away. Is that clear? So I don't really need to solve differential equation for that. And P in this case, hat in this case is going to be equal to I sigma divided by alpha d psi hat minus U hat. Sorry, wrong one. U bar d psi hat plus psi hat du bar touching the plane, which can be written in all right. So that's what we have for pressure. So pressure is given explicitly by this expression. Okay? So we are going into sort of algebraically heavy category here, so land here. So if you feel overwhelmed with algebra, just let me know. Sometimes it takes a few seconds, just breathe and talk about something else and come back, because otherwise your brain might just switch off. Okay, so let me know when you reach that point when you cannot take it anymore, and we will just do something else briefly and then come back. Are still okay? Still able to follow what I'm doing here? Okay. So now 5 minutes left, so all right, we will just struggle for another 5 minutes and then we will have well-deserved rest. So let us take now these expressions and substitute them into equation for let's take this and substitute it into equation 4. Now, let me see where we can put it in. So, into here. Okay, so we used this first expression, we took pressure out of there. Now let's put it back. So essentially what we are doing, we're using a standard elimination procedure, right? So we take the first, use the first expression, equation to make one of the variables a subject of it. And once we are done, we substitute it into the second equation. So that's how you solve linear system of equations, like what you do in primary school. Except now we apply it to differential equations. So nothing fancy here, a lot of algebra and a lot of writing, but that's, in principle, it is very simple procedure. Okay. Ooh. Yes, so we pretty much finished with our time, right? Recording time. So I'll just make a comment. And we will stop for a while because I also need some rest. I'm stumbling. So what we are trying to do now is to take this expression from the first equation, substitute into the second one. So we already know that the continuity equation is gone. Stream function will kill it. And what we would like to do is to essentially have one equation which does not contain p. And we are successful in doing that. So we will take it out of here, substitute it there, and p will be gone. And the last equation will be also gone. And whatever is left is something which we will need to investigate. Okay, so let me just maybe write the last thing. So if I do that, if I do what I just described, take this, substitute it there, ignore this, we will get the final result, which reads like that: u bar minus I sigma divided by alpha multiplied by d squared psi hat minus alpha squared psi hat minus psi hat d squared u bar is equal to 0. So that's what I was aiming to get before we go for the well-deserved break. Okay, so once again, pressure is expressed. Then I take this expression and substitute it into the second equation. So I need to differentiate it with respect to z. Once I do that, I will substitute it, and that's what I will get as a result. Okay? So this is called Rayleigh equation. Rayleigh introduced it. What do you think? How old do you think this equation is? So just your guess. When do you think people were able to do all that without any computers? At how long time ago? Anyone? Any guess? So what the first digit, which millennium? First millennium, right? So, or second millennium rather, 1. So hundreds. 1, 2, 3, 4, 5, what? 8? Okay, 8. Well, good guess. All right, so not many people can do it now, right, with the age of computer. But now, this is a famous Rayleigh's equation, so which is derived for describe stability of inviscid flows, right? At this stage, we still have not defined what u of z is, right? So we just know that it is some function, but we didn't say what it is. But we know what will happen to this function. So we will know what the perturbation are going to do. So, and these perturbations will be described by this equation, and sigma is their complex amplification rate. So sigma could be either, can have either positive or negative real parts. And that's what we will be exploring for the rest of today. So we derived the main equation, now we will need to actually try to solve it. We'll do that in the second half of this class, so I will need to spend 1 more hour essentially deriving the algebra for you. And after that, after I finish, I will ask you to actually solve the equation for a certain type of problems. So you will see how the algebra works, right, by just doing the algebra yourselves. And I would ask you to pay attention to what we do today, because again, if you do it yourself, so expect this to be in your test, right, in the final test. So pay attention to what we will be doing, especially in the last hour today, because that will be essentially the same thing I will ask you to do in your on your final day. Okay? All right, have a rest and come back refreshed.